My name is Javier Camara from the University of York, and I'm going to present this joint work with Bradley Schmerl and David Garlan from Carnegie Mellon University, entitled Software Architecture and Task Plan Co-Adaptation for Mobile Service Robots. Autonomous mobile service robots are becoming an increasingly important application domain, where robots are tasked with missions that have to be carried out satisfying a set of non-functional requirements that might involve aspects such as safety, timeliness, or energy efficiency. This slide shows a simple robotics scenario that we're going to employ to illustrate the concepts presented during the remainder of this talk. In the scenario, we have a small mobile robot that is tasked with a simple mission of moving to a specific location within a building, marked by the green star in the picture. This robot has to accomplish this mission while satisfying different non-functional objectives. The first one is accuracy, that is, it should be able to conclude the mission in a map position that is as close as possible to the target location specified. The second one is timeliness, so it should try to minimize time to completion. And the third one is safety, meaning that the robot should be able to navigate the physical space as safely as possible. This might entail, for instance, minimizing the chances of collision against walls and other obstacles found in the corridors. In the context of this scenario, a solution to the problem is a pair that contains two elements. The first one is what we call an instruction graph, which is simply a specification of the actions that the robot should carry out to complete its mission. The second one is an architecture configuration of the robot, which is a specification of the set of components, parameters, and how they are connected at runtime to enable the functionality of the robot. Mobile robots can often operate under different configurations by including alternative functionally equivalent components such as sensors, localization, and collision avoidance algorithms that result in different non-functional trade-offs. However, obtaining the best combination of architecture configuration and task plan specification is not straightforward due to the mutual dependencies between them. In general, the outcome of executing the same mission specification, for instance, reaching the target location through a specific path, in different software configurations will differ depending on factors like energy efficiency of the configuration or safety aspects related to the accuracy of the sensors and navigation algorithms used. Conversely, adapting the task specification, for instance, when the robot needs to find a new path because an obstacle is blocking the way, might require reconfiguration because the current architecture configuration may not be suitable for the new path. For instance, because these might include dark corridors in which camera-based navigation is not an option anymore. In this context, how do we go about selecting a solution that satisfies our objectives in the best possible way? This question doesn't have an obvious answer. Although the example we have just described is in the domain of autonomous mobile robots, many other classes of self-adaptive systems increasingly need to consider adapting both structural and behavioral aspects of the system to achieve their goals. Accounting for dependencies in decision-making for adaptation poses a challenge because of the size of the combined solution spaces for the architecture reconfiguration and task replanning. These can easily become too large to be adequately explored at runtime. Dividing and conquering the solution space can address this problem. In fact, existing work like the reference architecture morph propose employing different solvers to synthesize control for structural and behavioral aspects of the system separately, and then include a negotiation process to match behavioral and structural specifications to make sure they can be safely used together. For instance, if an architecture reconfiguration is synthesized separately from a robot task plan, this a posteriori negotiation should make sure that the target architecture configuration includes all the components required to carry out the actions needed by the task plan. However, although full separation of concerns increases scalability, there is a trade-off with optimality and the provision of warranties about the solutions obtained. This is because dependencies between architecture and tasks need to be considered if we want to be able to optimize for and predict the outcome of adaptation in a given execution context. To address this issue, we propose an approach that employs separate solvers for behavioral and structural adaptation aspects. In this approach, however, problems are not treated independently, and solvers are coordinated at planning time, effectively co-adapting architectural reconfigurations and task plans. Our approach to architecture and task plan co-adaptation is based on the MAPE model, and specifically, it is designed to be integrated as part of its planning stage. Our approach assumes a set of domain models in MAPE's knowledge base that capture different aspects of the domain, such as the software architecture of the system, tasks, or resources such as energy. From these models, we are able to extract pieces of information that are employed to populate formal model templates that are then used as input to different formal analysis tools integrated in the planner. Concretely, our approach is instantiated using Alloy and the probabilistic model checker Prism. These are used in tandem to reason under uncertainty both about the functional correctness of the adaptation plans generated as well as about non-functional aspects of correctness, which are analyzed quantitatively. In our mobile robotics domain, the different models that we have are the following. First, we have the architecture model, which contains a formal description of the architectural style of the system, as well as a set of available components at runtime, and the reconfiguration primitives that can be used to change the robot's architecture. Next, we have the physical environment model, which is encoded as a graph where nodes correspond to map locations and arcs designate valid robot trajectories among them. These nodes and arcs are tagged with relevant attributes, such as map coordinates for locations or distances among them in the case of arcs. The task model contains a summary of the current state of the mission's execution, as well as the set of primitive actions available for the robot to execute. Finally, the resource model, which corresponds to power in our robotics scenario, can be used to query the remaining amount of energy in the battery, as well as to predict the amount of energy required to execute a robot primitive in a given configuration. Now that we have presented the main characteristics of our approach and the set of models we have in our adaptation domain, we are going to provide an overview of our approach, which is divided into two planning pipelines that take care of synthesizing architectural reconfigurations and task plans, respectively. The first stage in the architecture reconfiguration pipeline consists of generating the set of legal architectures available in the current execution context. To do that, the configuration synthesis model generated component receives as input the set of components currently available in the architecture, which are obtained via the monitoring infrastructure of the MAPE loop, as well as the formal description of the architectural style. With those elements, it encodes an alloy specification. That alloy specification is then used as input to the architecture synthesizer component, which employs alloy to instantiate legal architectural configurations. The second stage in the architecture reconfiguration pipeline generates reconfiguration plans to adapt the robot software architecture. In this stage, the architecture reconfiguration model generator component receives as input the set of legal configurations produced in the previous stage, as well as the set of reconfiguration primitives available from the architecture model. From the resource model, it obtains the predicted energy consumption required for those reconfiguration primitives. From the task model, it receives a set of task attribute quantifiers, which enable quantification of non-functional aspects of tasks like overall energy consumed or probability of collisions against obstacles during a mission. These are encoded in this case as temporal logic formulas that enable a probabilistic model checker like Prism to quantify these task attributes. Using all these elements, the model generator component produces a specification that is used by the architectural reconfiguration planner to synthesize a set of reconfiguration plans employing Prism's MDP policy synthesis capabilities. This concludes the steps that correspond to the architectural reconfiguration pipeline. For the task planning pipeline, the first step is generating a set of candidate legal plans to complete the mission. In our scenario, These plans are sequences of legal actions to move between two arbitrary locations in the map. We will informally refer to these as paths. The path preprocessor component receives the current robot location and the intended target location from the task model, as well as information about the physical space topology from the environment model. The component employs then Dijkstra's algorithm to generate all legal paths between the robot's current and target locations. This step is introduced as an optimization of a performing path synthesis via model checking, which is much more expensive in computational terms. The last stage of the task planning pipeline performs the analysis of all candidate task plans, which include both a path and a reconfiguration in which the path will be traversed to complete the mission. The first step of this stage is generating a set of candidate task models, each of which is encoded as an MDP Prism specification. To produce this set of specifications, the task planning model generator component receives the set of legal paths generated in the previous stage, as well as the set of legal reconfigurations obtained from the architecture reconfiguration planning pipeline. Legal paths are ranked by a heuristic, which in this case is distance minimization, and a configurable amount of top-ranking candidates are extracted to be encoded into one of the Prism specifications for a candidate solution. Each one of these Prism specifications also contains a set of symbolic actions that represent each possible architecture reconfiguration plan. All these actions are encoded in a non-deterministic choice of the MDP. For each candidate solution Prism specification, the task planner uses Prism in the backend to resolve the non-deterministic choice of architectural configuration via MDP policy synthesis. The policy is synthesized to optimize the task attribute preferences specified in the task model. Finally, the policy that better satisfies the task preferences is selected and translated into a task plan that is sent over to MAPE case execution stage. Our approach was evaluated on a scenario in which an augmented Turtlebot was used to traverse corridors within a large building. This Turtlebot runs on ROS and is equipped with multiple sensors and software components that can provide similar functionality and can be enabled or disabled at runtime, for instance, whenever a reconfiguration is needed because a component fails. With respect to hardware, this Turtlebot is equipped with a headlamp to light dark corridors. This is very inefficient in terms of energy consumption, but can be useful when only camera-based navigation is available. The robot also has a back camera that is used to identify wall markers, also used for camera-based navigation. Although this does not work well in the dark, it has excellent energy efficiency and good accuracy when it comes to obstacle detection. The LiDAR is able to perform a depth scan on a plane. It has a reasonable efficiency and works well in the dark, although it's not good at detecting obstacles that do not intersect with the LiDAR scan plane. Finally, a Kinect sensor is able to provide both 3D point clouds and camera images. It has an excellent energy efficiency, it is good at obstacle detection, and it works well in the dark. It is worth noting that the Kinect requires an additional transform component to convert 3D point cloud data into LiDAR format, which is the one that can be consumed by the rest of the software components in the robot. When it comes to software, we focus on variation of different localization components available in ROS, which have different energy and performance trade-offs. The standard in ROS is the Adaptive Monte Carlo Localization, or AMCL, which has excellent performance and an optimized algorithm. Alternatively, we can use MRPT, which still has reasonable performance but is more CPU intensive. Finally, Aruco is a visual marker-based localization component which requires wall markers and multiple components to provide localization. It is CPU intensive and requires front and back camera images to determine the robot's position. To bring this all together, when the robot is trying to accomplish a task, environment changes, software crashes, or sensor failures could prevent the task from completing. We use a co-adaptation approach that coordinates alloy, prism, and path planning to derive reconfigurations. This planning considers dependencies between software configurations and task plans. It reduces the planning state space, but still constructs optimal plans. We have implemented this approach using the Rainbow self-adaptation framework. We customized probes, gauges, and effectors for raw systems, incorporated multiple models, and implemented our approach as its planning component. Rainbow runs in parallel to the robot software, discovering problems and finding and enacting reconfigurations as the robot executes its mission. To evaluate the approach, we wanted to answer two questions. First, we wanted to understand if the approach was tractable when used with real robot software. And second, we wanted to understand the quality and timing differences between considering co-adaptation, that is, considering both task and architecture reconfiguration planning, versus just considering architecture adaptations. To show tractability, we run the robot in simulation in a large number of scenarios in 3 cases. In the first case, called the base case or A case, we run an experiment with a starting condition and optimization goal, but without the adaptive infrastructure and without an event that would cause the robot to go into error. This gives us cases where the task is feasible with a given starting configuration and some metrics about task completion timing and accuracy. In the second case, or B case, we again run with the same starting condition as in the A case, without the adaptive infrastructure, but this time perturb the environment to cause the need for adaptation in the robot. Such perturbations included causing an active sensor to fail, causing the localization component to crash, or turning off a light, thus simulating an environment variation. In the final case, or C case, we run the robot with the same starting condition as A and B, the same perturbations as in B, but this time with the adaptive infrastructure. Each A, B, and C case forms a test tripod where we can compare mission success, timing, and accuracy between the same starting conditions and perturbations. In total, we collected 838 such test tripods with randomly chosen starting conditions, tasks, utilities, and perturbations. 646 times, the C case fixed the problem introduced in B, and in only 21 cases did C do worse. The remaining 171 cases showed no significant difference between the B and C cases. This shows that our approach worked to complete missions involving real third-party robotic software running in a realistic but simulated environment. We're going to see now an example of adaptation where both path and software are changed. In the map of the building where the robot has to carry out its mission, we can see some dark corridors in red and some corridors in blue containing obstacles that the robot has to avoid. In our user interface, we can set the starting location for the robot, as well as its target destination. We can also choose the initial configuration of the robot, as well as our utility preference. In this case, we're choosing safety. We can also display the path that is best suited to a particular starting configuration. These are displayed in blue. So for instance, for Aruco camera-based navigation, we can see how we can go through the corridor in the top of the slide. Whereas for MRPT LiDAR, the ideal path is the one that goes through the dark corridor in the bottom. We're going to choose MRPT LiDAR as the initial starting configuration for our mission. And when we start the execution, we can see how the robot starts moving and intends to follow the blue path that leads through the dark corridor in the bottom. However, we are going to simulate a failure in the sensor, so we're going to kill the LiDAR. And now the self-adaptive layer will have to find a new combination of architecture configuration and path to complete the mission. The self-adaptive layer finds 6 valid reconfigurations and 5 different paths to reach its destination. Now a new configuration is selected. The robot is reconfigured to AMCL Kinect, and here we can see how the path has also changed. Now the robot is going through the corridor in the middle with obstacles, In this case, the path has changed because it's the best suited to the new architecture configuration found by the self-adaptive layer. We're going to see an example of adaptation now where the disturbance is in the environment. Concretely, a corridor becomes dark. We're going to task our robot with going from L5 in the bottom of the screen to L29 on the top. We're going to choose camera-based navigation as our starting configuration, and we're going to favor timeliness. We start running the mission, and the robot starts moving towards its destination. Eventually, the robot is going to reach a corridor that is dark, so camera-based navigation is not usable anymore. At this point, the self-adaptive layer has to find a new combination of architecture configuration and task plan to reach the destination. Out of all the reconfigurations, the new architecture configuration chosen is going to be MRPT Connect that works well in the dark. Once the robot reconfigures, we can see that it continues through the same path it was on. In this case, note that the path hasn't changed because the path that the robot was on is still the best suited for the new architecture configuration. This contrasts with the previous example in which both the architecture configuration and the path changed when adapting. We also address the question of how much improvement co-adaptation provides over just considering architecture adaptation. In this evaluation, we only run the planner, but run it over a much larger experiment case of 74,400 scenarios, half of which considered co-adaptation, so the planner was free to reconfigure both the task and the architecture, and half of which only considered adapting the architecture. The results show that co-adaptation comes up with different plans and overall higher utility than considering just architecture alone. Consider the cases in which the robot started in a configuration using a Roku camera. If co-adaptation is enabled, the resulting plan selects the AMCL Kinect configuration 23.95% more times than when only considering architecture adaptation, and has on average 0.13 higher utility. In fact, the planner is unable to find the plan in 21.43% more cases if the planner is not free to reconfigure the task. More details regarding timing are in the paper, but overall the results show that co-adaptation is both tractable with real robot software and results in different and better plans than software adaptation alone. In this talk, we have presented an approach for architecture configuration and task plan co-adaptation that is able to consider both functional and non-functional aspects of adaptation planning. The approach proposes a separation of behavioral and structural concerns while considering their dependencies through coordination of separate solvers at planning time. Our results show feasibility in the area of autonomous mobile robotics, where the approach has been instantiated combining Alloy and Prism to build the different solvers. Moreover, our results also indicate a remarkable improvement over just considering behavioral or structural adaptation in isolation, or treating them as independent problems. With respect to limitations, our approach has been instantiated on a specific type of robotics scenario and mission. We plan to broaden the scope of our study to other types of robotic mission types and scenarios. We have evaluated our approach on an architectural model that abstracts away parts of the robot's architecture. Moreover, we plan to generalize our formal model generation mechanisms using model transformations instead of the current template-based approach. Our framework currently assumes a single architecture reconfiguration per task plan. Further work will address scalability issues induced by allowing multiple reconfigurations during the mission, as well as trade-offs with the potential quality improvements in adaptation plans. Finally, our evaluation has been carried out using the real software stack running in the robot and a high-fidelity simulation of its physical environment. Further work will evaluate the approach in a physical test facility.